Now that we have looked at the water potential, which essentially connects you to with bonded and unbonded both, and you look at intra as well as interatomic potential, and what we said again to make it very clear, interatomic potential is between oxygen and oxygen, because these are two molecules, intermolecular, and then intramolecular is inside the molecule, where you talk about different bond lengths and the torsional angle and the different kinds of angular bending and etcetera. So, that exactly what we were looking at is to find in a potential that will combine with the different kinds of ideas like protein structure, etcetera. So, if we move forward, now we are going to look at another model that is called atom potentials, and specifically when you have a molecular system, there are interactions between atoms. So, let us say if I do CH3 and C2H5OH, which is a alcohol molecule, and I took another C2H5OH, I have to have interaction between C and H, and there are 5 H and 2 carbon atoms. So, if I take 2 molecules of C2H5OH, and then I also have OH, which is one of the radicals in there. So, now we have to combine all these ideas. So, that is where you have cross interaction between the atoms. So, that is where what we look at here is atom-atom potential. So, in this case total potential is sum of atom-atom pair potential. So, the way it is normally simplified is that you take all these different atoms. In this case, if you look at your slide, then you have A1, A2, B1, B2, and then there is interaction between those pairs. So, A1, B1, A2, B2, A1, A2 and B1, B2, etcetera. So, all these interactions are specifically created as atom-atom pair potential. So, we will look at all these pairs, and as your molecule is rigid, in non-degenerate ground states interaction is weak. So, internal structure is weakly affected by the geometry, steric effect is important. So, what we are looking here is that in this case the assumption you can make, again it depends on what you are trying to understand from a molecular dynamics experiment, is that you can consider them as rigid molecules. So, now you do not have to deal with angle bending, angle torsion and length changes as you go through. So, one approximation in atom-atom potential is you just use pair potential between the atoms, but you consider the molecules as rigid, and that is one way to look at it. Now, if you look at perturbation theory, as r I j goes greater than the core radius, and you can see this core radius is given around these atoms. You can see these two atoms and their core radius, which essentially shows electronic cloud around them. So, now we can use perturbation theory for the core r I j, which is greater than core radius. So, we make sure that they are long range beyond the core radius, and electrostatic effects we use the multipole expansion, and induce effects by charge or neutral atoms. Now, we look at dispersion effect, which we look at as C6 dipole induced dipole, which is another dipole, because if you look at A1, A2 will generate some dipolar interaction because of the electronic cloud. When it interacts with each other, it essentially separates into positive and negative charge. So, it becomes like a magnet, and that is what is called two poles are called dipoles. So, those dipole interaction now come into play as the dispersion effects, and then short range effects, repulsion caused by the cores, that you can counter as an exponential function. So, these are the one is the pair potential r I j between r I and I j. Then you look at electrostatic expansion using perturbation theory, multipole expansion. Then you also look at induction due to the charge, and then you are looking also as dispersion due to the dipole interaction, which is electrostatic and magnetic dipole interaction, and then the short range repulsion is looked at by the exponential. So, if you create something like that, that will be an approximation that you can apply for certain situation. And these kinds of approximations are now used in silicon potential. As you know, silica is the most abundantly available material in the world. And if you look at the valley, which we call Silicon Valley, is coming from this name of silicon material, because most of the electronic instruments are made out of silicon wafers. So, these silicon wafers are essentially doped with different germanium and other impurities to create what we call semiconductor material. And that is why all the semiconductor industry that started in 60s and 70s and 80s in California, in San Jose area and San Francisco, that made what is called Silicon Valley. And so, if you look at the material silicon with the single crystal wafers, which is primarily the substrate or the basic material for all your electronic gadgets and instruments, is essentially doping that with lots of transistors and creating what we call as VLSI, very large integration of these devices. And so, very large scale integration VLSI essentially gives you what is called microchips. So, if you look at Pentium 5, which has so many terabytes and all of these now is reaching to gigabyte level of operation that it can perform in your computers. So, you go with the latest and greatest chip, which has lot of interaction. That means, it has millions and billions of transistors inside that small chip. And the small chip is responsible for all your television, the transistors, the electronic gadgets, everything that you can think of. And that is where you need to study silicon very well. So, now we are looking at silicon as the material which is called SiO2. So, there are two silicon, Si is one silicon atom and there are two oxygen atoms. So, H2O had two hydrogen atoms connected with oxygen, and SiO2 silicon atom is connected with two oxygen atoms. So, SiO2 becomes very important material for us to understand, and they have a particular way of connecting together, which is called tetrahedral bonding structure. So, if you look at a central atom and three dimensionally it has tetrahedral created, and that tetrahedral angles are then calculated. So, if you look at your slide now, solid silicon is not well described by pair potential. So, obviously, we have to come up with something better than pair potential in order to look at the tetrahedral bonding structure caused by partially filled p shells. So, as you know, the atomic structures have orbitals, and each orbitals are given names like s, p, d, etc. And those orbitals are the one which are based on energy levels, s being the lowest energy level, s, p, d and f. So, those are the higher level of orbitals, and if you look at those orbital, in this case is sp3 hybrid. So, it tells you that how many atoms are in that particular orbital. So, if you look at the distribution of orbitals in silicon material, you are looking at these partially filled p shells, and those partially filled p shells make silicon also have charge interaction. So, there is a short range potential caused by localized electrons, and then if you look at it is the stiff potential for short range interaction, and then there is also you have to take care of the electronic interaction due to the unfilled p shells. And that is where Stillinger and Tom Weber they came up with this idea in 1985 to create a lattice constant based system. So, they took at the empirical data which is coming from lattice constant, cohesive energy, melting point and the structure, tetrahedral structure. So, based on that understanding, they came up with silicon potential function. In this case, you can look at there are R I, R k and R j. So, if you look at here, we are looking at potential function V 2 R, and so you have one function for the distance between the silicon and oxygen atoms, and then you are looking at much higher terms which are calculating between the angle, the tetrahedral angle between the silicon and oxygen atoms, and in a unit cell there are a whole bunch of silicon atoms and the oxygen atoms around it, making SiO2 structure, a lattice structure, and that is what is looked at. Because it is directional, now you have to look at the directional bonding. So, what Stillinger Weber did, they looked at the pair potential, but they also looked at the potential of three atoms I, j, k. and that tri-atom potential was added in order to take care of the tetrahedral angle. So, think about different kinds of triangles connecting these tetrahedrals and making this full structure, and that is called Stillinger-Weber. So, if you look at your slide now, you see there are two potentials. One is V 2, which is for the potential with I j pair potential, and V 3, which is I j k. So, if you look at the pair potential V 2 I j has is eta, which is the potential energy. Then this function which takes care of R I j over sigma, which is essentially the lattice constant. Then F 2 r, which is the force here, is given by some form of what we call is the Leonard-Jones plus a formulation of component which is exponential type. And then V 3, you have now R I j, R I k, and J I k. So, if you go back, these are the R I, R k, and R j. So, these are the three terms. So, you are now looking at different terms for I j and J I, and I j and K I. So, you can think about 3 atoms, and you are going in cycles I j, J k, and K I. And now, for each cycle of I j, J k, and K I, we have interaction term, and these are 3 dimensional or 3 terms I j k terms. So, you are looking at each one bond lengths and the angle between them, and that is how this triangular model comes into play. And then you can also look at another term there, which is defining H, which is the interaction term for all 3 I, J, and K, and that is defined by exponential term, which talks about the bond lengths. And then also there is a rotational term which is defined by cos theta. So, now you understand that the whole idea here is there are different mathematical representations. You simplify them by intra and intermolecular interaction. For intra, you can use all the bond lengths and bond angles and all of that, come up with the right kind of geometry where you can use trigonometrical function like cos theta, exponential function, etc. And then you also have inter between, let us say, silicon and silicon. In that case, you are going to come up with a Leonard-Jonesian type or some kind of interaction which is taking care of some of the idea of lattice constant, cohesive energy, melting point, and the structure. With that understanding, the Stillinger-Weber came up with this whole idea about 3 V I j and V I j k, and that is how they were able to look at 7 parameters which are described in their potential function, which you look at in their reference that I provided you with the Stillinger-Weber function. What you look at the end of this section, I want to show you very quickly the comparison between the Stillinger-Weber model, which was created, and its version in which was done by Bruton and Lee, and they tested this potential function with the experimental results. So, if you look at T m, the melting temperature is 1691 by Stillinger-Weber, and experiment is 1683, very close, good prediction, but primarily because the potential was created with the melting temperature as one of the parameters. Now, if you look at the D, you are looking at different parameters here. In this case, diffusion constant, you look at 6.94. This kind of does not match well, is 10 to the power minus 4, while this is 10 to the power minus 5, but close. And if you look at then the other parameters like sublimation energy, etc., you can see that is not too bad. So, this is the whole point, is that if you come up with these experimental constants, and if you look at all these different constants like Cp, which is the specific heat at constant pressure, and you look at that 0.999 and experimental value is 1.04, very close. So, I think the whole idea about any potential function is that when you test it computationally and you calculate all these thermodynamic parameters, do you get a reasonable match, not exact match, because obviously it is a computational model, not a real experiment. But if the match between experiment and computational data is reasonable, then you are okay to use that to understand more complex phenomena involving silicon. And that is where it is very important that once a new potential function is created, it is tested and you calculate all these different parameters to understand that. Thank you.